Hey, good morning, chemists. So this is a walkthrough of task 5, very similar to the walkthrough that we did of your organic test. If you haven't looked at the walkthrough of your organic test yet and you want to see it, it's in exactly the same folder that this one's stored in, so you should be able to access that one. So make sure you've got a copy of your task 5 because you're going to want it, and also something to make corrections, so perhaps a different colour, pen, something along those lines. So, just like we did for the last walkthrough, we've got fake students' answers on the left and the marked schemes on the right. So all of the correct answers are the bits that are in blue and red. The reason that we've got the fake student, it just helps me to explain some of the finer marking points to you, so hopefully you find this useful. For this first question, the multiple choice question, the answer is B. This is just a standard bonds enthalpy calculation. So it's calculating bonds broken, bonds formed, and then adding these together. The idea that breaking bonds is endothermic, so it requires energy to be put in, and that making bonds is exothermic, so it has a negative value. And if you add the positive value to the negative value, you get your overall enthalpy change, which is a minus 125. So the common mistake here would just be accidentally getting those the other way around, so plus 125. I'm yet to work out how you get 140, but if you have got 140 and accidentally put C or D, do tell me. The second question is much more difficult conceptually. It talks about a situation where you're reacting some sodium hydroxide with some nitric acid, and the enthalpy change or the energy change of this experiment is being measured. So it says the temperature increases by 6 degrees. The experiment was then repeated using the same concentrations but half the volumes, and it asked you what would happen to the temperature change. So the immediate thing that you might think is, oh, there's half as much stuff there, so half as many moles, so it's going to be half as big. Okay. But what you've also got to remember is that the volume that you're heating is also been halved. So there's half as much energy coming out, but also half the volume to heat up. So the temperature change is going to be exactly the same. Okay. So although both the solutions have halved, the volume that's being heated is also halved. So it's just going to be exactly the same temperature. So, on to our final multiple choice question. This question is this type of question is very common. The idea that you talk about an experiment, a value is obtained from that experiment, and that value is different to what was expected, so perhaps different to that from the data books here. And here it says that the value was more exothermic than expected. So this is an enthalpy change of combustion experiment that's got a larger magnitude value for delta H than expected. The easiest way to tackle these questions is to write down the calculation steps that you would go through. So sometimes these questions are about titration, sometimes they're about enthalpy changes. So writing down the calculation steps that you would go through in order to answer these questions helps. Here you can see that what happened was that delta H was more exothermic than expected, so delta H was larger. So we need a change that either makes Q larger or N smaller. Okay, there's only one change that does this, and that's a B. It says in the calculation, the student used the molar mass of ethanol instead of methanol. If you use the molar mass of ethanol instead of methanol, it's going to make it look like less moles reacted because you're going to be dividing your mass that burned by a larger number. So N is going to become smaller, and so therefore delta H is going to become bigger. So the only correct answer here is B. Question 4 then, we're on to the written questions. This question is an incredibly common question. It's not really got anything to do with enthalpy change, but it's one that's worth reminding ourselves about. It says explain the meaning of the Roman numerals in the name magnesium nitrate 5. There's 3 things that you must have here. You must have that this relates to oxidation number or oxidation state. You must have that it's referring to the element nitrogen, not nitrate, okay, specifically nitrogen. And you must also have the plus 5, not just 5 plus 5. These Roman numerals are always telling us about the oxidation number of, in polyatomic ions like nitrate, phosphate, carbonate, any element attached to oxygen, and the oxidation number that it's telling you about is always positive. So here, oxidation number or state of nitrogen is plus 5, and all of it's necessary. My students told us about oxidation number of nitrogen, but they haven't told us the fact that it's plus 5, so unfortunately we don't get the mark here. So this next calculation, someone's carried out an experiment in order to calculate the enthalpy change of the reaction that we just talked about, and it's involving some silver nitrate and some magnesium. The temperature readings were given. You can see that my students clocked that this is exothermic, this is worth doing, and they've then been asked to calculate the enthalpy change of the reaction using this information. So this is a standard Q equals mc delta T, and then calculating moles, and then calculating delta H question. So for Q equals MC delta T, you should be using the 25 centimetres cubed of solution multiplied by 4.18, which can be found in your data sheet, multiplied by 28, which was the temperature change. And this should give you 2,926 joules. My student's done this correctly, so they've got 1 point. Okay, 1 mark just over here. The next mark is for calculating moles. This is a concentration calculation. You've got a concentration, 0.512 up here, and you've got a volume, 25 centimetres cubed. There they are in my calculation. We've got to also remember that we need to convert this volume to decimeters cubed in order to correctly calculate moles. So it's 0.512 multiplied by 25 over 1,000 gives you 0.0128 moles. Okay. The final mark is then for calculating delta H, which is enthalpy change per mole, the energy change per mole. So we need our energy change or energy transferred. We need it in kilojoules, not joules. So we need to divide by 1,000, and then we need to divide all of this by moles. So let's have a look at what my student's done. My student's forgotten that they need to divide by 1,000 here, and they've also forgotten that they need to divide by 1,000 here. So although they've got the right answer, okay, minus 229, they haven't carried out this calculation correctly, so unfortunately they are just limited to the 1 mark that they achieved for the top part of the question. Check yours carefully. It's very, very easy to write down the correct answer and have made both of these errors and it doesn't count. Okay? You need to do each step correctly. There is error carry forwards. For example, if you've got your if you've calculated moles wrongly, but then have gone on to do the calculation part of delta H correctly, then that's fine. The answer must have a negative sign, but you don't just get a mark for a negative sign. You need the actual calculation to be carried out correctly in order for this to be awarded. So, final question. In this final question, on this page, it says at the end of the experiment, the student added a few drops of aqueous sodium chloride to the reaction mixture to test whether all of the aqueous silver nitrate had reacted. Explain how this would show you whether all the silver nitrate has reacted. Include an equation with state symbols in your answer. So my students included the equation. The equation is correct, but unfortunately it doesn't have state symbols, so they don't achieve the mark. What we would see if the reaction was incomplete was that there would be some silver ions hanging around, and so we would see a white precipitate of silver chloride forming if we've added sodium chloride to this reaction. If the reaction is complete, that precipitate wouldn't form. Okay, so what we're looking for is that if the reaction was incomplete, or white, if you've mentioned the colour, precipitate would form, or if the reaction was complete, no precipitate would form. What we're not looking for is, if the reaction was complete, the solution would be colourless, because the solution is colourless all the way through the reaction. Okay, it doesn't matter whether the precipitate forms or not. If the precipitate's there, the solution is still colourless, and if the precipitate's not there, the solution is still colourless. So if you talk about colour of solution, it's just going to be ignored. What we need is the presence of a precipitate if the reaction is incomplete, or the absence of a precipitate if the reaction is complete. And if you mention a colour, it must be white. So my student said if the reaction was complete, then this would not be seen. And they've talked about a white precipitate, so they can have that second mark. So they've got 1 for both of these questions. So the next page, this is drawing an enthalpy profile. If you're asked to draw an enthalpy profile, there's a high chance that it's going to be for an endothermic reaction because they are more complicated to draw than an exothermic reaction. So 3 points for this enthalpy profile. Point number 1, you need your axes to be correct. So my student has got enthalpy, but they've made the common mistake that rather than saying progress of reaction, they've said time, so they don't achieve the first mark. So you need enthalpy and progress of reaction. This is just a comparative diagram. It doesn't need units or anything like that. Okay, I know it looks a bit like a graph. It's not, so it doesn't need any units. It's just comparative. The next mark is for correctly showing an endothermic reaction. So it's reactants below products, so the fact that you've got a horizontal line with your reactants drawn on it and a horizontal line with your products drawn on it, and also a correctly labelled arrow for delta H. This arrow must just have 1 arrowhead, and it must be pointing upwards, and it must be completely vertical. You need the bold substances, but nothing else. So the substances that my students included, so I basically just crossed them out, haven't I? That colour, that's very helpful. But the substances, there we go. The substances that my students have included, this is fine, okay? Their problem is that they've done this. Right? So if you've written the substances as my student has written them, that's okay. They're above in the equation anyway. It's just copying, so no points for copying state symbols. But If you have a double-headed arrow, this is wrong, so they haven't achieved the second mark even. And the last mark is for correctly labelled activation energy. This sort of curve that we draw on the enthalpy profile is there to represent bonds being broken in the reactants and then bonds forming to make the products. So it's kind of bond breaking, bond forming curve. And the activation energy is from your reactants to the peak of this bond breaking curve. So the amount of energy you need to break all of the bonds in the reactants. That's not what activation enthalpy is, but it's what it's representing in this diagram. Unfortunately, my students drawn it here coming from the products to the peak, so they also do not get the mark. So they, unfortunately, even though this looks like an enthalpy profile, don't get any marks for this question at all. Make sure that you've got yours. Again, this activation energy arrow, 1 arrow ahead, right? Not 2. So the next 2 questions are probably some of the more complicated ones in this whole task. They are a little bit tricky, and I think many people will have done what my students done and just gone blind with the Q equals MC delta T here because they've seen the words energy transferred. So a cool pack contains a mass of sodium nitrate. It was activated. The temperature of the cool pack decreased by 16 degrees C. Calculate the energy transferred in kilojoules when 2.6 grams of ammonium nitrate is dissolved in excess water. We've got an amount of ammonium nitrate here, and we've got a value for delta H up here. So what this question is asking us to do is not to do Q equals MC delta T. You don't have the right information to do this anyway. It's about adjusting the value of delta H, which is per mole, to a specific amount of ammonium nitrate. So our first mark is for working out moles of ammonium nitrate, and so the MR of ammonium nitrate is 80, and so our moles should come out as 0.0325. Okay. The next mark is for adjusting this value of delta H so that it represents 0.0325 moles reacting rather than 1 mole, so it's just as simple as multiplying them together. So you get 1 mark for calculating moles, and as long as it's clear that you have calculated moles, whatever your calculated value of moles might be, multiplied by 22.4 gives us our answer, which should be 0.728 kilojoules. My student doesn't get either of these because they haven't calculated moles, they've just kind of thought energy transferred, or let's stuff some numbers into Q equals MC delta T, and so unfortunately nothing for this one either. And they've got completely confused on the last one, which is unsurprising because what they've done up here doesn't help particularly much. So it then says, using this answer, calculate the mass of water present in the cool pack, give your answer to 3 significant figures. So a bit of insight, I've got a bit of hindsight in this question. I wrote this question, so apologies if it confused you. I also think that this shouldn't say mass of water. So I'm going to change it for future years to say mass of solution. We'll come to that in a second. This is a rearrangement of Q equals MC delta T. So we've got our value for Q now. We know the other values for the other things going on. What we're trying to work out is the mass of water present, or the mass of solution, I probably should say. So if we rearrange Q equals MC delta T, taking into account the fact that Q needs to be in joules, not kilojoules, we should get 10.9 grams of solution. If you have taken away the mass of the solid from this to leave the mass of the water, then you may also have the mark. So if you've gone further than this and actually done what I asked, then good for you. You can still have the mark. I will correct this so it says mass of solution for future years. So next question is a Hess cycle. So first part is about a definition, so what is meant by standard enthalpy change of combustion. Standard enthalpy change of combustion, you need to mention 1 mole of something being burned in oxygen. Okay, so a mole of something, burning or combustion, oxygen. Okay, those are your 3 things. My students got it's the energy released when 1 mole of a substance combusts completely under standard conditions. So unfortunately, they haven't mentioned the oxygen, so nothing here. They've also completely forgotten to do the second part of the question, which says give the standard conditions. The standard conditions that you must mention are the temperature and the pressure. 1 mole per decimeter cubed is a standard condition, but it's not relevant here because there are never going to be any solutions for enthalpy change of combustion. So if you've mentioned 1 mole per decimeter cubed, it's just going to get ignored. You just need these 2. Okay, that's the second one. This question, you have a Hess cycle and you've been asked to use your Hess cycle to calculate the enthalpy change of combustion of pentan 2-ol, and the information that you've been given is enthalpy change of formation. It's enthalpy change of formation that determines the shape of the Hess cycle and also the substances in it. So what we're going through is the imaginary process of making all of the reactants and products for our top reaction out of their elements in standard states. So you must have elements in standard states in this bottom box, and that includes their state symbols. So although my students have written the elements, they haven't got the state symbols. They've also made the really common mistake that because there's 7.5 O2 here, it's really easy to accidentally write 7.5 O2 here. But don't forget, there's an oxygen here as well. Okay, and that oxygen also needs to be taken into account. So it is 8O2. That's a really common error. This drawing of the hair cycle, arrows being the correct way around, all the rest of it is worth a mark. The next part is for working out what goes on each of the arrows, or working out what goes on one of the arrows, because it requires some calculation. So it's really for this part of the calculation, that's this part. Okay. If you've written 5 times minus 3 times 4 plus 6 times minus 286, that is minus 3,686. And if you've gone on to get the right answer, you have evaluated this correctly, so you can have this mark. So where it says minus 3,686 seen anywhere, if you've done the correct calculation and you've got the right answer finally, so the minus 3320, you've done this, you can have this mark. The next mark is for the final answer, so it's just the opposite of the first arrow plus the second. So here we want minus 366 plus all of this lot. My students forgotten the minus and minus, so this has gone a little bit wrong, but they have done this, so I would accept that for that second mark. Unfortunately, this hasn't gone quite right, so they haven't got the right answer at the end. But they have recognised that it should have a negative sign. Because this is enthalpy change of combustion, these colours don't work. Because this is enthalpy change of combustion, and we know that the final answer should be negative, there is a mark for this negative sign. Provided you've done some form of calculation to get here, you can have that mark. Okay, and it's more a mark for common sense, knowing that combustion should be negative. So the next question is a standard Q equals MC delta T. So you're provided with a whole load of information. The only difference with this Q equals MC delta T versus many others is that it's looking at a different method of calorimetry. So rather than our coffee cup calorimetry where everything's happening in the same vessel, here we have calorimetry for an enthalpy change of combustion. I don't think any classes are lucky enough to actually get into this practical before we had to abandon the college site. You may not have done this practical in class. If you're in a future year group and watching this, then hopefully you will have got to do this practical in class. There's a little burner here with some combustion going on, and this is being used to heat some water in a container. This container might be a beaker. Quite often this beaker is made of metal, so that the heat energy conducts effectively into the water, and it's the temperature changes of water we're measuring. So here, because the water is very separate from the reaction, it's really clear that the mass of what's being heated is just this water. So, first part of Q equals MC delta T, make sure that you use the mass of water, which is 180 grams. Don't do what my student did, which is use the incorrect mass. It's a very easy mistake to make. So you should get a very large enthalpy change. We would expect, or energy change. We would expect this to be very large. Enthalpy change of combustions are huge, okay, big numbers, always in the thousands of kilojoules per mole. So we would expect it to be a fairly large amount of energy that's being transferred. Don't be put off by this. The next thing you need to work out is how many moles of pentantal oil you've burned in order to do this. My students got the molar mass slightly incorrect. So they have tried to calculate moles, but they've got the molar mass wrong, so just make sure that yours is 88. And then the final mark for this is for delta H. So this is your value for your energy transferred in kilojoules divided by your moles gives you your correct answer. And here my student has done their value for their enthalpy change in kilojoules, and they have done their moles, and they have given an answer, and they have recognised that it should be exothermic, so they have a minus sign. So actually, although they've fluffed up the first 2 marks, they can have the third. Okay, from error carry forward, just make sure your answer has a minus sign. It doesn't come out in the calculation, it's for you to look at the data and think, yes, the temperature change is going up. So you need to make sure that you're always making that little check every time you're writing a value down for delta H, particularly from Q equals MC delta T. It always has to have a sign. Okay. Now there's a couple of questions about the experiment itself. So the calculated value of enthalpy change of combustion from our in-class experiment was lower than the value obtained by calculation. Okay. Apart from heat loss, there are just 2 reasons for the difference. It's quite strict about how we describe the differences here. Heat loss covers everything from heat being lost to the apparatus, to the specific heat capacity of the apparatus, to heat being lost to the surroundings. All of those things come under the So large heading off heat loss. So we can't mention any of those things. What we're left with is incomplete combustion. Incomplete combustion releases less energy than complete combustion, so it's going to have affected our value for delta H. So this would be the one that I would immediately look at. Evaporation of fuel has been hinted at previously in the paper, and it's actually a really huge problem, particularly for petrol cars in the summer. We blend our petrol in order to try and limit this, and it still accounts for a huge proportion of emissions. I think at one point, going back a little bit in the past, probably when I was teaching about this about 10 years ago, we used to say it was about 15% of vehicle emissions in the summer from petrol cars was down to evaporation of fuel. It's certainly going to be happening in this experiment as well. And you could also say the experiment was not carried out under standard conditions. This is more suspecting rather than knowing, because it didn't tell you the experiment wasn't being carried out not under standard conditions, but if it's in a classroom, it's quite unlikely to be perfect. It certainly seems like the starting temperature is a little bit low for standard conditions. So you could say non-standard conditions. So my student says incomplete combustion, and also about the equipment absorbing heat. Unfortunately, this is heat loss, but they do get a mark for incomplete combustion. So that's good news. The next question asks you about a different fuel, methanol, and it asks in terms of bond breaking and bond making, why this is an exothermic reaction. This is such a common question. You need to get the idea that bond breaking is endothermic and bond making is exothermic somewhere in your answer. And you also need to get the idea that more energy is being released than absorbed. Okay, so here my student says the reaction is exothermic as it released more energy when making bonds. Okay, this is telling me that making bonds is exothermic than it took to break them. Well, I'd accept this as a reasonable answer. It doesn't have the words endothermic and exothermic in it. If I really wanted my student to polish up their answer, I might insist that they include these terms, but I'm actually happy to award this. The idea that more energy is released when bonds are made than was taken when bonds are broken is what we're aiming for here. So if you've included the words exothermic and endothermic, great, but the key thing that you've got to watch out for is the fact that it's very easy to make it sound like both bond making and bond breaking are endothermic. So more energy was needed to break bonds than was needed to make them, something like that. It's very, very easy to accidentally say this. So read your answer back really carefully. Have you made it clear you know the differences in energy change related to bond making and bond breaking? So this next question is about bond enthalpies. It's asked what's meant by average bond enthalpy. So here we have the energy change when a mole of covalent bonds is broken homolytically in the gas phase. That's what my student said. This is a very nice definition for average bond enthalpy. All we're looking for is breaking 1 mole of bonds in gas form, so in gaseous molecules. This definition that my students provided mentions specifically covalent bonds. I actually quite like this. Bond enthalpies are for covalent bonds. We don't want to get these confused with talking about any other weird kind of energy changes related to ionic bonding, which is what we've talked about for the entirety of Pack 5D. So I quite like this addition of covalent, and if you haven't got this in your answer, I encourage you to put it in, even though your answer wouldn't be marked wrong. It is also by homolytic fission. It doesn't make a massive amount of difference, but if you've included the fact that it's by homolytic fission, great. Okay. So what we're really looking for is the idea that it's 1 mole of bonds being broken and it's in the gas form, which my student very definitely has. In fact, we have a super answer to this. This has 2 marks, so it's the 1 mole bit and then the gas molecules bit, so 2 points. In a modern exam question, this would not be worth 2 marks, just 1. Okay. It's a very generous past paper. I've copied the equation in just so that we can see what's going on here. Here you've been asked to calculate the bond enthalpy of the carbon-hydrogen bond in methanol. The easiest way to do this is to write an expression that describes your bond breaking, bond making, and delta H, basically. So an expression for delta H, including bond breaking and bond making. Here, the marking points may be a little bit confusing, but this is really the expression that we're going for. Okay, the idea that our delta H is equal to all of the bonds broken with a positive sign minus all of the bonds made. The bond that we're interested in, the carbon-hydrogen bond, is broken. It's in the methanol, and there are 3 of them. So that's why you've got this 3x here, is that there's 3 of them. So what we're really looking for is a positive 1,550 for all of the other bonds that are broken, a negative 3,466 for all of the other bonds that are made, and then evaluating this expression and linking them to delta H. So the idea that minus 6,803 is equal to this expression, so if we rearrange this, we get 3x equal to this value and then x being equal to this value. Essentially, the final mark is for dividing by 3. So even if you haven't got anywhere near this, if you've divided by 3 somewhere, you get the final mark. If you've tried to sum up your bonds broken and bonds made, effectively you get the first and second mark. And the third mark is we're writing an expression that links this to delta H correctly. So if you've accidentally made a mistake up here and up here, but you've linked it to delta H in a similar way that it's done here, you can get the third mark by error carried forward. My students made 2 classic mistakes in this. Firstly, they've completely forgotten the oxygen. Okay, this is a really, really common mistake. People get hung up on all the bonds in the methanol, and they do carbon dioxide and water, and they completely forget about the 1.5 O2. So that's what my students done here. The other thing that they've forgotten is the 3x. Okay, so they wouldn't achieve the final mark. They wouldn't achieve the first mark because they've missed the oxygen, and also they have not included a sign, so they can't achieve the fourth mark either. But they have written the correct expression for the second mark, and they can have the second mark, so they get 1. Okay, for that one. So this is the longer level of response question. There's a model answer to this question. I'm not going to dwell too much on the actual marks that you might show it on the next page, to kind of use it to evaluate my fake student's answer. Let's run through what you should have done. You've been provided with a whole load of information about various energy changes. Constructing the Hess cycle that's going to be used to calculate the energy change from reaction 6.1 is definitely the most challenging thing in this question. So reaction 6.1 is the one that's running across the top, that's this one. Okay. And what we have to do is use reaction 6.2 and reaction 6.3 to kind of link together in order to form an appropriate Hess cycle to find the enthalpy change from reaction 6.1. These energy changes are not straightforward, okay, they're quite weird, so they're all different to each other, and we just need to kind of use our common sense. Reaction 6.2 starts with sodium oxide, so we've got some sodium oxide here, so it would make sense for that to be this reaction. And it shows sodium oxide reacting with water to make sodium hydroxide. So there it is. Okay. You can see that the HCl is just sort of hanging out, okay, not doing anything. That's fine. Okay, we've seen this in Born-Haber cycles, and it's absolutely fine for something to not change and just sort of be chilling out there. We did have to add some water in order for this reaction to happen, but bearing in mind that this is an aqueous, there definitely is water available. Our second reaction, let's use green for that one, then shows NaOH and HCl reacting together to make the products that we want to make up here. So that's this reacting with this. Okay. You'll notice that there are 2 NaOH and 2 HCl making 2 of our products up here, and also only 1 water. That's because we had to take in a water here, so it's cancelled out by the time that it comes out here. But really, you can see that 2 lots of this process are happening. Okay. So we've created our Hess cycle where we've got our reaction 6.1 going across the top, we've got our reaction 6.2 going down the left, and we've got our reaction 6.3 happening twice going up at the right. This is really tricky, okay, so don't get cross with yourself if you haven't spotted this. It is awkward to fit together, it just takes a little bit of trial and error. My advice would be look for one of the reactants on the left, see if you can spot it. Here in reaction 6.2 we've got our sodium oxide, see if you can spot it and see if you can use that to start to fit the cycle together. For reaction 6.2, we've then been provided with a massive amount of information that we're going to use in order to do Q equals MC delta T. It's all raw experimental data, so there's obviously some evaluation that we have to do to work out exactly what masses and temperature changes and things that we want to include. Once we've done that work, we should have Q equals MC delta T using the mass 25.75 and using the temperature change 35 in order to give us 3.767 kilojoules of energy being transferred. If we're calculating moles, similar thing. We want the mass of substance heated. Oh, that's terrible. I'm not going to see that at all. Which is 1.24 grams. Dividing this by the molar mass to give us 0.02 moles. And if we put all of that together to find a value for delta H, we should get minus 188 kilojoules. So all this top bit is just about attention to detail. Okay, so the mistakes that are made here are just typically transposition errors, people using the wrong mass in the wrong place. Very occasionally, I have seen students use the mass 25.75 and then have added on the sodium oxide. But remember, this is a mass of the solution. It already includes the mass of sodium oxide, and we shouldn't be doing this anyway. We should only ever use the mass of wet stuff when we're in Q equals MC delta T. So mass of solution being the gold standard, mass of water being an approximation if we are making a solution, but never adding a solid mass onto a mass of water, and even worse, adding a solid mass onto a mass of solution. The solid's already been taken account of in there. So if we then put this value and the value that we've been given down here for reaction 6.3 into our calculation for our Hess cycle, we should come to minus 303. Okay. The marking points for this, I can show you on the so this is a level of response questions. This is what teachers are confronted with when we have a look at the mark scheme for these types of questions. The bit that should really concern you is this bit, okay, the right-hand side, which is known as indicative scientific points. These indicative scientific points talk about all the things that you could have mentioned in your answer that would have been correct. Okay, so all the relevant information that you could have mentioned. And essentially, you want all of this. Okay, every time you're checking your work for one of these questions, it really doesn't matter whether you've got 3 marks, 4 marks, 5 marks, or 6 marks. What you want is to have covered all of this. Okay, so if you're missing any of these points or haven't included units or haven't made certain things clear, add them in. Okay, and then next time that you do this question, you'll be better prepared. In terms of how the marking works, this is the left-hand side is the bit that concerns me, and here, let's have a look at my sheet's answer and we can see where they fit. So you can see they have constructed the Hess cycle correctly, well done, but they haven't included 2 lots of our other reaction on this side. They haven't done this in the calculation here, it's down here, no 2 times. For Q equals MC delta T, they have made this weird mistake that I talked about, adding everything together. And other than that, they have carried this out correctly. They have correctly calculated the moles, and they have correctly gone on to calculate delta H and recognise that it's an exothermic reaction. So they've essentially made 2 mistakes: a mistake in the mass that they've used in Q equals MC delta T, and also a mistake using their Hess cycle that they have drawn it. To me, this is something that attempts to describe all 3 scientific points over here. They've done the whole question, they've given it all a go, so they've attempted all of these indicative points, but the explanations will be incomplete. And there is a logical line of reasoning, absolutely, but there may be some minor errors in the calculations for delta H and also the energy change. But to me, this completely describes this level 2, and I would give them 4 marks. Okay, so on to percentage errors. Just a couple of things to bear in mind with percentage errors. Firstly, take into account the number of times that you read the equipment. Okay, that's very important. So for all of these measurements, we read the equipment twice. And also, make sure that you take into account what readings you're using. The readings should be the ones that go on in your calculation or that you use in your calculation. So temperature change, mass change, whatever it is that you're trying to work out that you're then going to use in your calculation. So these 2 values here. My student's done this correctly, but has missed out the multiply by 2 in both instances. Notice a little mistake in the mark scheme here. We don't want divide by 100, we want times by 100. There we go. So if you've missed off the 2 multiplied by 100s, or you've missed off the 2 multiplied by 2s, but have done the rest of the calculation correctly, you can have 1 mark. Do try and make sure that you include units in your percentage errors. They are percentages, so units is appropriate. If we wanted to suggest a modification to the experiment that used the same apparatus which would reduce the percentage errors in the measurements, then you would need to use a greater mass of sodium oxide. Okay? The greater mass of sodium oxide would increase the temperature change because more would be being reacted, and it would also increase the uncertainty with the mass measurement. So we want to say use a greater mass of sodium oxide, and you also need to mention that this would increase delta T. So it's likely that you might have said use more sodium oxide because this increases or decreases the error in the mass measurement, but you also need to say and would result in a larger delta T, or and would reduce the percentage uncertainty in delta T. So it's a change that affects both. Okay. It says it draw references to repeating the experiment. This doesn't make it any change the percentage errors at all. It just gives us greater confidence that we haven't got an anomalous result. Reading to more significant figures is changing the equipment, so no, we can't have that. We can't also have increasing the volumes. If you increase the volume of water that you use, This is going to make delta T smaller, so because you're going to be heating up a larger volume, and therefore it's going to increase by a smaller amount. So it's actually going to make the experiment less, or have a higher percentage error as a result, which we're not keen on. So this question again, the 2 marks, 1 for the mass, 1 for the delta. So, question about hexane. You've been asked to write an equation with state symbols for the enthalpy change of formation of hexane. Just watch out for hexane's state at room temperature and pressure. This tells us it should be a liquid, so you do need those state symbols for this equation. It is very difficult to determine the standard enthalpy change of formation of any organic substance, indeed many things, directly. Suggested reason for this. There's all sorts of reasons for this. My students gone with the idea that there are lots of molecules with the formula C6H14, not just hexane. This is a tenuous, ish description of this top point, where there are many different hydrocarbons or isomers would form, not just hexane. I'd be inclined to allow it, but it could be improved just to make it clear that they know that all of these isomers would be forming if we carried out this reaction. We wouldn't be able to carry out this reaction anyway, because it actually would not be feasible under these conditions. We can go have a think about entropy and Gibbs free energy in order to explain this if you've got that far in the course. You could also say that the activation energy of this reaction would be ridiculously too high, or the reaction would be slow to measure. It basically wouldn't work in the lab. So we either want that it's not feasible, the activation energy is too high, or the reaction would be too slow. And also, even if the reaction did work, it's not just going to form hexane, you're going to form a myriad of other things. For some unknown reason, this is 2 marks. This has always been a 1 mark question. It's probably my mistake. So you can give yourself the bonus mark here. It's just 1 mark's worth of marks that we're looking for. And our final question, as far as I remember, the standard enthalpy change of formation of hexane can be determined indirectly. This time we're doing the opposite of the Hess cycle that we saw before. We're doing the standard enthalpy change of combustion Hess cycle to work out formation. So we want downward arrows and combustion products at the bottom because we're using combustion data. Remember, the data determines the setup of our cycle. Okay? That's very important. You don't need to include the oxygen on the arrows. I like to for completeness, so I can know that everything is a balance and I've done it correctly. The marking points are for this calculation, okay, be it evaluated through your final answer or be it evaluated somewhere on your page. They are for calculating the correct final answer, and they're also for knowing or working out that this has a negative sign. Again, this negative sign, you shouldn't know that this reaction is negative. Okay, there's no way of staring at something and thinking, oh yes, this enthalpy change of formation is going to be exothermic or endothermic, because you've got one's breaking down, one's making. It's not that straightforward. So there's no way of staring at it and knowing. This negative sign, it has to come from calculation. Okay, so you can't just write -5 and not do any calculation and then get a point. Okay, it needs to be through calculation that you have got the sign. It's really rewarding writing the sign with the correct answer. So think of it that way. If you've done a calculation, even if you've made mistakes, but you've written the negative sign because you know that delta H needed a sign, that's what it's trying to reward. Hi guys, hopefully you found that helpful. I'm sorry if it's ridiculously long, but hopefully you find that a useful run through of your task. Obviously, if you've got any questions, surgery is your place to go. We're here to help you. So thank you for watching.